umbrella. It's not. I don't think it currently is, but it was.
Yeah.
You never know.
You see how more things so
Yeah.
kids were exposed before about 15 it's at best
Get some use out of it, I'm sure.
it's good to use. Yeah,
Yeah.
Yesterday I went to the parade for Halloween for my daughter. There's this someone I was carrying laser spurred.
Oh yeah.
It seems a lot loud. Actually,
That your daughter Princess Leia?
what that?
That your daughter Princess Leia?
No, she was not. But because I had the umbrella, I was carrying. The one you put too much attention was that I was carrying. So no, what? She just was a night. And yet, yesterday evening was very nice. My mother was dressed as princess, the medieval princess, and we took the dog, and we took some kind of wing. The dog looked like a dragon. The whole family was equipped for medieval princess.
Yeah.
All right, let's get started, at least for the introduction, while people are joining us. Before introducing our speaker today, let me remind you of the events this week and next week. We do not have a lunchtime talk this week because we are organizing the conference dedicated to Jim Woodward, my dear colleague, the conference is Friday and Saturday. It starts at 9:25. On Friday. Yes. I know that's a little bit strange. It starts at 9:25 because Mike Dietrich will make an introduction. You are invited to register on the center website, but if you haven't done it, of course, it doesn't really matter. You are invited to join us anyway. So there is no lunchtime talk, but the conference dedicated to Jim on Friday and Saturday. Next week, we have a week off in terms of talks and lectures here at the center, not in terms of philosophy, because next week is a very busy week. HPS and philosophy are organizing the Salmon lecture given by PGS at 3 p.m., I believe, on Wednesday on induction. And then, as you know, Thursday, Friday, Saturday, the PSA is taking place downtown. So that's going to keep us busy for the whole week doing philosophy of science. And we'll be back in action the week after that for two events early in the week. On Monday from 10 to noon, Reed and I will be organizing a reading group with Denis Borsboom, who is both a philosopher, a psychologist, and a psychometrician. So we have some of his work on theory in psychology and theory and measurement. So if you're interested, please email Reed and me, and we'll put you on the mailing list. And on Tuesday, the 15th, Reed will be giving her lecture. That's the event for the coming week. There it's my great pleasure to introduce our speaker, Adam Koberinski, who is a postdoctoral fellow at the center, and we've been very happy and lucky to have Adam for already a few months. He worked in the philosophy of physics very broadly, but more precisely on the history, methodology, and foundations of quantum field theory and cosmology as well. Adam has got his PhD from University of Western Ontario, which is University of Western now, no?
Sort of.
In between, depending on the day.
Not officially,
no,
but
okay.
yeah.
So it's the University of Western Ontario, and he has published in literally all the best journals in philosophy of science, philosophy of physics, studies, philosophy of science, foundation, EGPS, and so on and so forth. It's a very on a range of topics such as the constants, the nature of physical constants, cosmology, quantum field theory, and so on. It's a really great list of publications. And today we're going to be hearing about philosophy of dark energy. Floor is yours, Adam.
Great. Thanks, Edward. Yeah, so This talk is based on a paper that I'm writing with Bridget Falk and Chris Smink. The audience is quite different for the paper. This is a paper that's going in a special issue of a physics journal to explain to cosmologists why there's some why they should pay attention to philosophy, at least in relationship to dark energy. So the structure of the talk is going to be a little bit different from how I have structured the paper, but I think a lot of the overlap's the same because I mean, besides the few of you who have some background in philosophy of cosmology, this is kind of doing the opposite. It's telling philosophers why they should pay attention to cosmology, maybe. So I think that there's a lot of overlap in content. So I thought it'd be fun to kind of switch that around. The outline for the talk, I originally had an extra section here. I realized this morning when I was kind of running through my talk that I would not have time for it, but it's down at the end. It's on typicality assumptions in cosmology if you're interested. But to start, I'll talk about what dark energy is. The standard model of cosmology known as the lambda CDM model and the status of lambda. Lambda is the cosmological constant, which parameterizes dark energy. Then I'm going to talk a little bit of general philosophy of science background and applying it to cosmology to figure out, can we give it this sort of new, these new entities that we've discovered in cosmology, and how should we think about them philosophically? Is this a sign of a good research program? Is it degenerating? Are these additions ad hoc? Are they justified? So kind of do some general phil sci background to get an general account of methodology, at least in physics, and kind of apply it to cosmology. Then I'll turn to some current ideas for explaining dark energy. So giving a theoretical account of what dark energy is and constraining dark energy. So this is on the observational side of trying to constrain or understand what its properties are and constrain the limits of possibilities. And then there'll be some conclusions at the end. So for those of you who maybe paid close attention to the title of the talk on the website and the title of the talk here, I changed it slightly. It was, I think, philosophy of the cosmological constant before. I changed it to philosophy of dark energy to avoid some confusion. The subject matter, the abstract was still correct. I've written on the cosmological constant problem, which might have, for those of you who have some background in here, might have thought that's what I'd be talking about just based on the title. This is a talk from the side of observational cosmology. This is not, I'll touch very briefly on the cosmological constant problem, but only as like a one slide. There's some problems with this particular explanatory strategy for understanding dark energy. So yeah, if you're interested in that, I've got some papers up there and I'll list them again at the end. Okay, so we'll start with, it's philosophy of dark energy. I'm sure some of you have at least heard the term dark energy, but I'll talk a little bit more about what dark energy is supposed to be. This little graphic here. So we've got this sort of picture of the evolution of the universe going up in time. Towards the end, you see it looks like space is expanding faster. There's sort of a curve here. Roughly speaking, dark energy is what's responsible for that accelerated expansion of the universe. Yeah, so I'll get into that. So first, what we know about dark energy, and then a lot about what we don't know about dark energy. So this is still kind of cutting edge frontier physics. We have a good observational case for it, but not a really good understanding of what dark energy really is. But what we do know, given our current standard model of cosmology, that dark energy makes up a large fraction of the mass energy density of the universe, about 70% of all mass energy density in the universe. So it's, there's a lot of it, whatever it is, by some metric. It has negative pressure, and so it drives the accelerated expansion of the universe. So it's kind of, pushes things apart rather than most matter and energy sources gravitationally kind of clump together. So you get, stars and galaxies and planets and all that sort of stuff. Dark energy is the opposite. It kind of pushes things apart. So it's driving the accelerated expansion of the universe. And for all we know right now is that it's perfectly consistent that whatever dark energy is, it can be parameterized by a simple constant that's added to the standard model of cosmology, this lambda term. And so that's, it could be that there's something underlying it, but it could turn out that it's just this sort of constant. And that's one of the things we don't know. We don't really have a theoretical explanation for what is sort of underlying this phenomenological parameter, if you will. Is it just a constant? Is it something that, you know, we've just fixed a constant of nature? Like, I don't know, for the solar system, we've learned how many planets there are. It's just it's something that, you know, it's just a number we fix in our model, and there's really nothing more to it. There's no deep underlying reason. Is it some new matter source, some exotic new type of matter that, you know, has properties that are quite counterintuitive? Does it signal the fact that we need to add this huge amount of energy density of something we don't know? Does that signal that maybe our theories of gravity are breaking down on cosmic distance scales? All these are live possibilities, and we don't really know. We don't really know any of the properties of dark energy. It's kind of again, other than it's these things I've listed on the left, there's really not a whole lot that we know about it. So it's one of these things that's recently discovered, new theoretical entity in some sense, and we're still in the process of either trying to work out the details or even deciding if there are any details that we need to work out. So I said it's parameterized by this constant that we add into the lambda CDM model of cosmology, this lambda term. Where does this lambda term come from? Is it, you know, is it this new parameter that we've like fudged in by hand afterwards? Is it sort of naturally there? I'll give a little brief history here. So right after Einstein published his general theory of relativity, he had the Einstein field equations, he had this desire to construct a model of the universe. It was kind of the first cosmological model that really, you know, engaged with our best theories of gravity. He had these sort of Machian intuitions that the space-time geometry should be entirely determined by matter. And in order to do that, for technical reasons, you need to have a closed universe. And he thought that, you know, cosmology, the universe, whatever it is, it's some big static entity, so it shouldn't be changing in time. And in order to get his equations to work out with the matter sources and the wanting a closed static universe, he needed to add this additional constant into his equations. There was nothing forbidding that constant. It's completely like allowed by all the symmetries, but it wasn't sort of in his initial formulation. Called this term the cosmological constant. That's stuck around. So you see in the equation here on the left-hand side is sort of the original form. So G mu nu is encodes the space-time geometry and curvature. That's the Einstein tensor. And T mu nu is the stress energy tensor. That's the matter content. And so there's some way in which the space-time and the geometry co-determine each other. And this kappa is just the strength of the gravitational interaction. So what Einstein did was introduce this new term. The lowercase g is the metric. The big G is defined in terms of the metric in some indirect sense. So it's not the G isn't the new part, it's just the lambda. And he worked this out to try to create a static universe. Well, it turns out that the introduction of this term wasn't at fault. Einstein saw this as like a big blunder of his. His solution, his particular cosmological solution is unstable. If you perturb the matter distribution just a little bit, you'll either have a universe that ends up collapsing on itself or something that expands off and isn't static. And this is why he called it a blunder, is because by putting this term in and trying to fudge this and not catching this instability in his solution, he failed to predict that the universe actually evolves in time, that the universe, at least now that we know it's expanding, but he could have predicted that, you know, generically we should expect the universe to evolve, either expand or contract. Hubble discovered that about a decade later. So Einstein called this his biggest blunder, which kind of put a negative spin on just the cosmological constant generally. So it was kind of relegated to the dustbin of history for a couple decades. You know, oh, Einstein made a mistake. The equations really shouldn't have this cosmological constant term in it at all. But by the, you know, late 60s, early 70s, we start reviving, you know, having a pretty worked out model of cosmology that is based on treating the universe as roughly homogeneous and isotropic on very large scales. So it kind of looks the same everywhere. The metrics that are used here on FLRW, it's Friedman, Lemaitre, Robertson, Walker, the people who discovered these solutions to the Einstein equations. And these, you know, generically allow for expansion, contraction, whatever. But it turns out that, you know, as we got more and more information on the theoretical side, it kind of made sense to introduce lambda again back into the equations to account, to kind of make sense of structure formation and have galaxies and galactic clusters and things like that form on the right timescales. based on what we thought, we had evidence that we think, the universe is a finite age. It's changed. The actual age we think it is over time has changed, but roughly 13.8 billion years. In order to have structure formation happen in sort of the right way that's consistent with everything else we know, cosmologists thought, oh, we should actually reintroduce this parameter. It's kind of, so it's sort of you could think of it maybe at that point as sort of like a theoretical fudge factor. We know the universe really isn't homogeneous and isotropic, so maybe there's we're not getting the detailed physics right, but this model still kind of works if we introduce this new parameter. But there's not really any observational evidence that it's needed into the kind of late 80s, early 90s. But finally, right at the end of the 90s, we get these observations of distance redshift relationships for a type of supernova called type 1a supernova. What a distance redshift relationship is, so supernova are kind of, the term that astronomers use is standard candles. They kind of, when stars explode, the right type of stars, they do it in a certain way, and they give off very particular light patterns. And so you can kind of get an idea of how far away that things are based on the exact pattern of the light. And it turns out that if the universe if space-time is sort of expanding or contracting in time, the light emitted from a supernova, if space is expanding, but as light's traveling, it kind of gets stretched out because it's traveling through space. So the light will be redshifted to a different frequency, if blue shifted if it was contracting. And the amount of redshift that you get, depending on how far away something is and how far back in time something happened, can give you an idea of the expansion history of the universe. Turns out that not only is the universe expanding recently, but the expansion is accelerating. And in order for that to happen, given what we know about the matter content of the universe, that gave a real direct observational case for this cosmological constant term. There's something there there's some other matter energy density present that is causing expansion to accelerate. So that's sort of, by the late 90s, you get something like direct observational evidence that something parameterized by lambda has to exist, not just, it works to kind of fudge our theory in the right sorts of ways. So it goes from being, relegated to Einstein's biggest blunder to back to being a central part of observational cosmology. And yeah, more recently you get that's continued. It's not like these are the only measurements. We have more precise supernova measurements. We have more precise observations of the cosmic microwave background, which is the sort of thermal radiation that pervades the universe. Not only its uniformity, but some of the small deviations from uniformity that it exhibits. Other things like baryonic acoustic oscillations. There's lots of different sorts of bits of evidence that kind of converge that maybe aren't as direct as a supernova, but sort of are independent lines of evidence that there's got to be something like a lambda term in our standard model of cosmology. So we have a pretty good case that there should be a lambda. What lambda is where we're confused. Is that we've got a strong case that given what we know about cosmology, that there's got to be something out there, but we don't really know how to describe it theoretically other than just with this constant term. So the standard model of cosmology is called the lambda CDM model. You can see lambda plays a very central role. It's the first thing in the model. But there's still some debate even amongst cosmologists, amongst theoretical physicists, about how exactly we should sort of interpret this. This is just another graphic of the age of the universe. It's fun giving cosmology talks because you get to put lots of fun pictures. Not so much. It's harder to visualize things in other areas of physics, but cosmology is nice. So there's this shift. We've introduced a lambda term. I've been slipping kind of back and forth between lambda, cosmological constant, dark energy. Lambda and cosmological constant you can literally take interchangeably. Dark energy seems to imply that there's more to it than a constant, right? Is it just a good piece of branding maybe? Or is there something more? I think it sort of reflects the idea that cosmologists expect that lambda, just having a constant in there is not the final story, that there's some physics underlying that we should hopefully be able to discover. Again, one sort of naive way of formulating that or putting that forward is so if you're looking at the matter energy density distribution in the universe, we have this pie chart. Ordinary matter is all the stuff that we know about non-gravitationally. Protons, electrons, more exotic sorts of particles that are smashed together at the LHC, but everything that we've kind of are able to detect terrestrially. Then you have dark matter. That's something that behaves kind of like normal matter. It clumps gravitationally in the normal sorts of ways. But as far as we can tell thus far, it only interacts gravitationally. We've never detected it any other way. So it's something that we have to introduce into our model to account for structure formation and to account for things like galactic curve rotation and things like that. But outside of cosmology, we don't have independent evidence for its existence. Dark energy, even weirder. We don't, it's, at least with dark matter, we know it's some kind of normal type of matter that clumps gravitationally. Dark energy does not have that property. It's, like I said, it drives accelerated expansion. We don't really know what dark matter is. There's some plausible candidates. We really don't know what dark energy is. But if you look, so this lambda CDM model, lambda being dark energy, CDM stands for cold dark matter. Cold just means it's not moving relativistically. There's some constraints on the properties of the dark matter. One way of thinking about it seems like we've gone really wrong. We've tried to apply general relativity to the universe as a whole, understand what's going on out there, and sure, yeah, we could, it's perfectly plausible that we could discover new matter or energy sources that we couldn't find on Earth. But the fact that ordinary matter includes sort of the exotic things that we typically think of, like black holes, like quasars, like all those sorts of things. The fact that 95% of the matter and energy density of the universe is something that we really have no independent evidence for, and really we've only learned through this model. Some philosophers, some cosmologists, some theoretical physicists take that as evidence that maybe we're doing something a little bit wrong here. Maybe this lambda CDM model, it can accommodate a lot of data, but really when we've had to put in 95% fudge factors in some sense, that's maybe that's a problem. Maybe this is a really clear sign of bad science. But to be fair, again, it does account for a lot. It accounts for, we can use the lambda CDM model to understand structure formation, like formation of stars, galaxies, galactic clusters, the existence of the cosmic microwave background, its structure, and very fine-grained structure, like the small, minute deviations from isotropy that we observe. I said large-scale structure, abundance of light elements, so things like the formation of atoms in the early universe, the formation of light elements and the relative abundances in the universe. All of these things fit well within the lambda CDM model. And of course, accelerating expansion, if you include dark energy. And yeah, so this is just my background. I've already said that it's perturbed FLRW space-time with these different matter components. So yeah, you might want to, is this ad hoc? Like I said, 95% of mass energy is things that we only really know about through the model itself. So yeah, in some sense that seems problematic, perhaps. So you'll see sometimes in popular accounts of cosmology from people who are voicing sort of minority opinions, because the majority view is obviously that this is not ad hoc. If that was the majority view, this kind of wouldn't be called the standard model of cosmology. But you'll see this sometimes framed this way. This is we need to look to philosophy of science and find out this is just bad science, right? This is an ad hoc research program. It's degenerating in some sense. We're just curve fitting. We're adding new parameters in, and maybe the curve fittings worked really well so far, but it's still something like curve fitting. And so more specifically, when we think about dark energy and the cosmological constant, so far everything just seems like it's compatible with it just being a brute constant in the equations. Should we be looking for some underlying explanation? If we don't find one, if it turns out that everything seems to be compatible with a pure constant, is that maybe then evidence that we've gone wrong somewhere and we need to start again and come up with a new model? So all these things, kind of motivate. Let's turn to philosophers have thought a lot about these sorts of things, about research, what sort of moves are acceptable in science, whether they're ad hoc, whether they're degenerating, et cetera, et cetera. So let's turn to that and try to come up with an overall account of the methodology of cosmology. So, talk about some kind of, the way I framed it to start draws on maybe like Popper and Lakatos, maybe a little bit of Kuhn. I'll talk about those briefly. I'm sure you're all familiar. then Stein, I'll talk about an account of science that I quite like, kind of an amalgamation of works of Howard Stein and George Smith, looking at sort of historical developments of physics, and then apply that to cosmology. So, maybe you want to start thinking, okay, we're going to take a step back. Let's think about what's a good methodology of science. We know from the past 50 or so years of philosophy of science that might be far too broad of a question to have say anything meaningful, right? Is there a scientific method? Is science unified in the right sorts of ways, or different sciences use different ways of investigating the world? So maybe, I'm just looking at cosmology. I don't need to ask, can I come up with a unified account of all of science? So let's phrase it as, what is a good account of successful scientific or physical practice that captures many of the features of modern cosmology? So regardless, I've kind of framed it, maybe the introduction of lambda and dark matter are ad hoc, but there's a very strong observational case that, from the 60s up until now, on the whole, cosmology has been quite successful. We've learned a lot about our universe that we didn't know 60 years ago. So in some sense, if you look at it, on a long enough time scale, we'd have to say that cosmology has been a successful sort of research program, even if it's running into problems today. So that's my starting point. If you want to say that cosmology has always been unjustified, then that's a separate sort of issue. So rephrasing the question, so what's a good methodology for cosmology? One thing you might think is, should we ask the cosmologists themselves? You're not probably going to get a very, I'm sure most of you know, doing philosophy of science and asking working scientists to give an account of their practice. You might not always get sort of ideal answers. As philosophers of science, we've learned to kind of, as Katie said yesterday, to listen to what the scientists do and not what they say necessarily. But as a first pass, maybe that's fair, maybe in broad strokes, but maybe not. It doesn't mean you can't find philosophically interesting work. So one account coming from a very minority view from Merritt, who's writing a book on Mond, which is an alternative to dark matter. He has a very philosophical, there's this whole book on philosophical approach to Mond, where he claims to draw on philosophy of science to argue that this is a better research program than that predicated on dark matter. And while his sort of account may be atypical, if you ask sort of working physicists, which I've done a little bit, about philosophy of science and the methodology of science, you'll probably get, at best, one of these three. So Popper is kind of the main one, some sort of Popperian account of what good science is. Sometimes Kuhn, usually Kuhn is brought up as a criticism, using Kuhnian terms to criticize a dominant paradigm or framework. And then sometimes even Lakatos as being a little bit more sophisticated version of Popper. So I'll just kind of quickly go through those because, and I'm sure this is all familiar to you. So, we've got Popper, propose a risky new hypothesis that sticks its neck out and makes falsifiable predictions, then go try to falsify it. If it doesn't, if it's falsified, throw it out, start again. If it's not falsified, continue to test it until it is falsified. And it's never confirmed, but it's corroborated. So I'm sure we all know this, is too strict a standard. We shouldn't be throwing out theories whenever they make one false prediction or something like that. But there's something kind of useful about this idea of making risky hypotheses, things that are, trying to, stick the neck out rather than just accommodate and, making sort of ad hoc corrections to accommodate anomalous results. So something about that seems kind of right. And what about Kuhn? Some of the key things that I think are important from Kuhn, something like the theory latedness of observation, that we kind of have to have we assume a sort of theoretical background that sort of structures our view of the world, whether that's a deep theory or even just sort of folk theory. There's, we have our own sort of background concepts that we use to when we make observations, which kind of also undermines this idea of direct falsification. And thinking about science temporally. So I've kind of already hinted at that, thinking about the overall practice of cosmology over time as being largely successful. So it's harder to make these decisions about whether one particular instance in isolation of the rest of the historical context or contemporary context is a good move or a bad move. You kind of have to take a fundamentally temporal view. But there's drawbacks to Kuhn as well. So we have, I think, things like incommensurability and the implied metaphysical constructivism that comes with his sort of view seem too strong. I think that, a lot of science, at least physics, is still quite grounded in empirical content that plays a very fundamental role. And I don't think there's that much incommensurability between actual rival theories, as Kuhn would have said. Well, the idea of like a paradigm is kind of suggestive and interesting. It's also kind of too rigid and constraining. There's not usually just one dominant paradigm that everybody's kind of enforcing. There's often sort of competitors. Scientists are a lot more flexible than Kuhn might have thought at the time. So yeah, so takeaways so far from Popper: we want sort of risky new moves made in science, whether we're proposing new theories or new components to a model. From Kuhn, we also realized that our observations are theory laden, and something like a paradigm kind of helpfully constrains the space of possibilities. Maybe not a paradigm itself, but we kind of try to play this balance between like risky new empirically testable hypotheses, but also that kind of fit within the frameworks that we're working in. So Lakatos, again, kind of I think that the most important part here is thinking about research programs rather than paradigms. So you can have competing research programs going on at the same time, thinking about whether they're degenerating or progressive over time, and thinking about that as a sort of temporal process. I think Lakatos maybe takes it a bit too far, that you really can't do any in situ assessment of theories. It's always kind of looking back and rationally reconstructing and saying, in the past, this was a successful paradigm and this wasn't. So that's not super useful for thinking about dark energy today. But again, we can think about this idea of, rather than thinking about, falsification or things like that, we're looking about whether we have some sort of progression or fruitfulness in the program. Cool. So that leads to this. So Howard Stein and George Smith, it's kind of an amalgam of their views, but I think they have a lot in common. So this 2010 paper by George Smith is actually really interesting general philosophy of science paper, kind of advocating for really understanding established and settled science and how we, how that plays a really important role in confirming theories and generating secure knowledge. It's not always things that are like proposing new theories. It's the sort of what do I have here? That sort of mopping up work, as Kuhn calls it, of normal science, is where we really generate the strongest justification for any claims to knowledge in science. He said, well, in physics, I'll narrow the claims to physics. And that one of the key insights here is that there's a sort of mutual interplay between your theoretical background and the phenomena, and that you use the theory to predict phenomena. When you see deviations, that motivates you to include more details in that you think are physically relevant on the basis of your theory, and get a sort of tighter constraint. And that these, things like that are really stable discoveries that come over time, like the orbits, like the orbital behavior of the planets around the sun, things like that are very stable, much more stable than the theories that are used to make those predictions. So, we still trust all the predictions and believe all of the causally relevant factors from Newtonian gravity for the predictions of the orbits of the planets and small perturbations thereof, even though we think that Newtonian theory is ultimately wrong. So applying something like that to cosmology, is this, can we think of as a test, I said overall, I want something that overall treats cosmology as fruitful or successful in some sense. I think the little pieces I've drawn from Kuhn, Popper, and Lakatos, and then this work of Stein and Smith kind of says yes. So we have these constraints in our theories of gravity, but also nuclear physics and particle physics that come into talking about the evolution of the universe as a whole. We have this sort of simplified background solution to the Einstein equations, this homogeneous and isotropic solution, but then we can perturb around that to include more details, including things like structure formation. Using this model, again, just to reiterate, we've explained several features of the universe that we had no idea about before. So things like the cosmic age of the universe, structure formation on all levels from atoms up to galactic clusters, CMB, black holes, gravitational waves, accelerated expansion, galaxy rotation properties, the propagation of light. There's a ton of stuff we've learned. So in some sense, cosmology has been a fruitful enterprise up to at least the introduction of dark matter and dark energy, and then we'll kind of test here. And and the important thing there, yeah, increasing precision and with new tests where we've sent new instruments into the sky or use more sensitive terrestrial instruments. We're redetermining the same parameters with more precision or determining them in independent ways, and they're converging on a lot of the same results. So the free parameters in the lambda CDM model, I mean, there's some tensions in places, but overall it's been converging with ever more and more precision onto consistent values. So sort of applying this account, what can we say about the cosmological constant? So again, thinking about things temporally, I want to say that on its own, just the idea of reintroducing lambda into our standard model of cosmology in order to explain the supernova data, that's something that we can't really assess just on its own as a one, in isolation of the rest of cosmology. So on its own, it's neither ad hoc or indicative of problems. We have to kind of see what comes after that, and that's kind of where I'm going to go from here. So the introduction of this new parameter, does it lead to more fruitful lines of inquiry? On the observational side, I want to say yes, for sure. We've found clever new ways to determine holding other things fixed or making other observations to constrain the value of the cosmological constant. And it seems we have a lot of constraints that kind of fit together to give a largely consistent overall value. On the theoretical side, it's a little bit less clear. So again, has it been fruitful? It's led to a lot of research of, okay, well, what could explain dark energy? If it's not just a constant, what could there be? And I think this is where we're kind of still in an open area, and there's a lot of room to have differing opinions on what the right way forward is, or if there's really any way forward. Yeah, so the obstacles, again, they're only detected through cosmology. We don't have fully independent tests. We have kind of independent lines of evidence within cosmology. But yeah, it's a little bit harder to overdetermine dark energy. Yeah, and so this is why it's sort of interesting for philosophers to get in. It's not that, it's not a clear case where like, oh, the people who are pursuing, this type of explanation for dark energy are clearly right and everybody else is clearly wrong. There's obviously room for some interesting disagreement here. So yeah, we'll move on to constraining and explaining lambda or dark energy. So I'll explain this graph, it'll come up again later, but this is one of the ways where you get observational constraints, holding other things fixed and making observations from different lines of evidence. You kind of converge on certain values. But we'll start first with, on the theoretical side, explaining the cosmological constant. So the first question is, is this a sort of term that demands an explanation? You'll see this sometimes in kind of the intro paragraphs of a review article on dark energy or something like that. Like, oh, we have this new mysterious term I've kind of motivated at the beginning too, where it seems like it's this exotic type of mass energy density, and it just cries out for explanation. There has to, you can't just leave it as is. But I don't think that's necessarily true. I think, what demands an explanation kind of depends on your sort of background assumptions and what you already know and what you think the correct methodology for cosmology is. So you might want an explanation, but it might not be something that demands one. So yeah, and there's a lot of openness here on the theoretical side that's not really fixed. There's room to pursue multiple strategies. And in terms of assessment of which avenues are more promising, usually, if in other areas of science, if there's a bunch of competing ideas, you go out and test them. Ideally, they make at least some different, distinguishing predictions. Ideally, you go out and make a sort of crucial experiment for that. That's sort of an idealized way of thinking about it. But then you can at least decide between competitor accounts. But that doesn't seem likely in the near future for dark energy. There's very little prospect for direct detection or observation of some exotic matter candidate that could be dark energy. It's not something that can be manipulated in the lab. It's really only observable on very large, like kind of cosmic distance scales. So it would be quite challenging to just kind of go out and say like, oh, well, I've got model A and you've got model B and they make these different predictions. Let's just go test them. That doesn't really seem to be the case. So we're going to have to in arguing for which one's better, there's going to be some, non-empirical or extra empirical arguments for that. So if we look elsewhere, or just kind of elsewhere in physics, I'm going to use Newtonian astronomy as an example, because that one I think is one, we can retrospectively look, and two, it's relatively clear, kind of the rules of the game and the stages that happened here. So if you encounter some new phenomena that's unexpected or that is not predicted by your current models, the first thing you want to do is try to, can we explain this new phenomena in terms of things we already know, in terms of things we already have? So for Newtonian astronomy, you might, if I'm trying to predict the orbit of the Earth around the sun, and I can say, oh, well, to first approximation, I can treat that as a two-body problem and get a pretty good idea. But I make more precise measurements, and it turns out, there's some disagreement between the actual observed orbits and what I'd predict based on that. Well, I need to factor in more causally relevant details, like the gravitational effects of the moon and of Jupiter and maybe of the other planets. And that's difficult, and you have to do numerical calculations, but you can do that, and you see a tightening again of or convergence again between what you observe and what you predict. So that's great. That's not a really mysterious case. We've just included more detail in the theory or something like that, and it's worked out. If that, that can work up to a point, but if that fails, maybe you need to add some new objects or entities or forces or something like that to your model. So for the classic example in Newtonian astronomy, that maybe works well for the Earth, but when I try to predict the orbit of Uranus, I can include all of the known factors at the time, and I'm still getting some persistent discrepancy. Turns out that discrepancy could be resolved if there was some new planet, Neptune, in the right position at the right time. We go out and we observe that. Cool. We've made, we've discovered a new entity, kind of theoretically, but we've then confirmed it. But that's sort of, you only do that kind of once you feel like you've included all the causally relevant details of things As a last resort, if that still doesn't work, like it didn't for Mercury for Newtonian physics, you might think, we posited Vulcan. We didn't ever observe Vulcan as a planet to perturb Mercury's orbit. Maybe thought, okay, well, we've tried new entities, we've tried known entities. Maybe our theory of gravity is not quite right, and we need to actually change the forces involved here, change the dynamics. And that turned out to work. Maybe not in the most straightforward way, but we moved to GR, and general relativity is able to predict that the anomalous motion of Mercury. So you kind of have like a hierarchy maybe that you might think of like steps to take when you have anomalous results that don't conform to your theory. You might try to include more details, add new entities, change the dynamics, and then who knows from there. But at least those three. But I'm going to start with a zeroth explanation, is that actually there's nothing to explain here at all. Maybe I've said from the observational side, we have a parameter, this lambda term that fits all the data, as everything's consistent with that being a true constant. Maybe we don't. The answer to does lambda demand an explanation is just no, it does not. It's just a free parameter, so that's a live option. And then explain with known features, new matter energy sources, or potentially modify gravity. So there's this kind of analogy here. And then a fourth option, which I'm not really going to touch on here because I just don't have time, is to explain away this phenomena. Maybe the assumptions that we're making in our models are actually, we're idealizing in certain ways, and those idealizations actually affect how we interpret the data in such a way that maybe there actually is an accelerated expansion overall. Maybe that's something I can talk about in the Q&A, but there's that's sort of a different approach rather than like trying to come up with new theories. It's trying to explain away, by de-idealizing or something like that. So for the first option, or zeroth option, who needs an explanation at all? A good resource on this is the Bianchi and Ravelli paper. It's just on the archive. It's called "Why All These Prejudices About a Constant." Their whole point is that there's really, from the side of general relativity, there's no puzzle here. This is just a free parameter. We fixed it. Let's move on. I mean, there's other theoretic on the quantum field theory side. There's still the cosmological constant problem, but they have a different sort of view about that as well. The sort of way this argument goes is that Einstein was wrong to call this a blunder. There's it's perfectly consistent with the symmetries of the theory. This is having the lambda term in there is the most general form of the theory. For a long time, we could get away due to the imprecision of our observations with treating it as zero. We've simplified the equations to treat it as zero. And now we've made new observations and we found out that we can no longer treat this as zero. You think maybe, again, going back to Newtonian physics as an example, you roll something down a plane to a first approximation, you can treat, if it's a smooth enough surface, or maybe you're rolling a ball or something, you can set friction to zero and you'll get pretty good predictions. But the more precisely you want to predict things, you're going to have to introduce friction at some point. Maybe lambda is just kind of analogous in the same sort of way. There's still some debate there of what kind of constant it is. Is this a contingent constant that varies, it's just some like the number of planets in the solar system, or is it something more like necessary, like the strength of the gravitational interaction or something like that? But that kind of comes up for a lot of constants in physics. Are these necessary, contingent? Can we, so there may be some desire to explain that constant in some way, but it doesn't kind of cry out in the way you might expect when we're talking about like, oh, there's dark energy that makes up 70% of the universe and we know nothing about it. No, it's just a constant. Maybe that has some further explanation, or maybe it doesn't. So that's kind of the deflationary account of we don't need an explanation at all. It's a live option on the table. Here's my one slide on the cosmological constant problem. So option one, which kind of seems like a dead end right now, was explaining things with known features. So the most obvious known feature that we could use to describe the cosmological constant comes from quantum field theory. If we try to merge general relativity and quantum field theory, we see that this term is the expectation value of vacuum energy density for each quantum field. When we couple that to gravity, it has the same formal properties as the cosmological constant term. It respects the same symmetries. It kind of acts as a constant. And so maybe we actually do have the resources on hand to explain the cosmological constant and just say it's actually, the cosmological constant is vacuum energy density. It's interesting in this sense because at least, barring things like spontaneous symmetry breaking and phase transitions in particle physics, this really would kind of treat it as a constant because that's the property of the vacuum energy density, is that it is, at least the expectation value is constant. So this would keep it as a constant, but give you some sort of underlying explanation anyway. Seems quite nice and promising, but then we run into the cosmological constant problem. We usually, we want our explanations to kind of make sense of what we observe. If this is an explanation for the cosmological constant, it's a really bad one. There's some properties of this vacuum energy density that are kind of problematic to a certain extent. In the way we calculate things in quantum field theory, this vacuum energy density scales with the fourth power of the sort of cutoff scale of applicability of the theory. So however high of an energy we think the standard model of particle physics works to, the vacuum energy density will be proportional to that energy scale to the fourth power. We have pretty good evidence that the standard model applies to quite high energies, at least to the energy scales that we've tested at the LHC so far, which is in the order of tera electron volts. If you take that as the sort of low, a very conservative estimate of the applicability of the standard model of particle physics, you get a value of the vacuum energy density that is 60 orders of magnitude, about 60 orders of magnitude larger than what we observe. It's a very, very, very bad prediction if it's a prediction or explanation. If you want to be more ambitious and say we think that standard model of particle physics should apply up until the Planck scale, which is where we have very good reason to think that quantum gravity effects will take over, then we get about 120 orders of magnitude of differences. That's again really, really bad prediction. If I'm trying to predict how, if Google Maps tells me that my destination is off by a factor of 10, that's really bad. Imagine being off by a factor of 10 to the 120. Like that's really, really, really bad. So again, this is a live problem. There's a lot of discussion about this on the side of thinking about it from the point of view of particle physics and from quantum gravity. At least in terms of describing the observed cosmological constant. It doesn't seem like this is going to work. Even attempts to solve the cosmological constant problem tend to be mechanisms that set vacuum energy density to 0, some new corrections. You could, again, have, there's solution attempts that try to leave a small residue left over. But then you get into issues of, unless there's a good explanation for why the small residue is left over, you have puzzles about fine tuning or something like that, potentially. So it doesn't seem like, regardless of what happens with the cosmological constant problem, it doesn't seem like that's a great explanation for the observed cosmological constant or the observed dark energy. So that one kind of seems like a dead end. Option 1, possible, but unlikely. So option 2, let's try explaining with new matter energy sources. So I've moved the cosmological constant to the right-hand side of the Einstein field equations here, and now made it not a constant. It can depend on, it can vary throughout space-time. So that sort of just suggestively indicates that it's a new matter source, because usually we put matter on the right for general relativity. We typically, the sort of simplest models treat the new matter source as some sort of scalar field, like quintessence models do this. And this is sort of theoretical progress. It's a correction to lambda CDM in the same way that, like, in some sense, adding a new planet is a correction to our model of the solar system. And so ideally, we can, that introduces new free parameters like the mass, that's the potential of the scalar field. So we're introducing these free parameters. We better hope that also brings in new observations that we can then to determine these free parameters, because that's, it's hard to define exactly what being ad hoc is, but we're puzzled about one free parameter and we now have 3 free parameters and we've only still explained all of the same things. That doesn't seem like we've made any progress. So insofar as observations are still fully compatible with lambda being a true constant, we have to search elsewhere potentially for new effects, new dynamical effects of this matter. It would really kind of force us to say, oh yeah, we're really onto something with these sorts of models. This is a live option, but again, still in early stages. Then finally, we modify gravity. So you might say, that these Einstein equations are wrong, at least at some level. One way to motivate this is that we observe the effects of the cosmological constant on very large distance scales, and far beyond where we have really good precision tests of GR. So perhaps what we're discovering is that general relativity actually just breaks down on really, really large scales, and maybe there's some reason to modify the equations. There's plenty of ways to do this. There's lots of different modifications. This is also a correction to our standard model. But the biggest problem, it turns out that it's really hard to make corrections on large distance scales that don't impact things on short distance scales in GR, at least to the level of precisions that we currently have. So you need to sort of introduce screening mechanisms into these models. So you might modify gravity and then have some sort of mechanism that screens off the new force or the new effects of the modified force on solar system type scales, and that goes away and leads to modifications on larger scales. And that seems kind of ad hoc. We've introduced a modification and then we have to find a way to like cancel out the modification in areas where we can make precise observations. But this is the same sort of open problems as with introducing new matter. We would need to find new compelling evidence that GR is wrong on those scales. So a couple options for explaining away is maybe, GR is still right. This is sort of, our model is wrong, but GR is right. Maybe, again, there's some issues with our modeling assumptions and idealizations that lead to some errors with matching observations that force us to introduce this fudge factor, kind of the way I was talking about it as a fudge factor at the beginning. One thing we know is that the universe is not homogeneous and isotropic on a lot of scales. We treat it as such on cosmic distance scales, but maybe that's an idealization that doesn't that actually affects our observations. For example, there's some toy models where we try to see how light propagates through inhomogeneous universes, where you like have a homogeneous background and you introduce like matter clumps through it. And it turns out that this would actually slow light and redshift light in a certain amount, but a very small at least as far as we know now, a very, very small percentage. So it's not quite enough to explain the supernova data. Another potential option is maybe, again, maybe the universe isn't homogeneous and isotropic. Maybe we're just near the center of a really, really big void. Like the overall density of the universe on average is some value, and we're in a very large region, or we're in a region of underdensity. How large it is a sort of free parameter that we could, when we try to fit to data. Turns out that it would have to be very, very large, like on the order of like 400 megaparsecs to 2 gigaparsecs, like very, very big void. And this actually doesn't do better than our current models. It fits the supernova data, but it doesn't really do a good job of fitting the cosmic microwave background or baryon acoustic oscillations. So it's not going to be an explanation that gets rid of needing lambda, really. And again, there's other options here. There could be other background assumptions that we haven't tested. So I think this is important work that's being carried out in sort of parallel with the work on trying to come up with new models. Because I think this is something that we need to do in all of our models, is have a sort of a way to handle the idealizations, at least have a sort of estimates of orders of magnitude of, how much are we how much are we messing with our predictions, given that we're making these idealizations. And that's something that I think is done everywhere in good established physics, at least, where we can get a handle on, how off are we going to be by neglecting these other factors. Okay, so I'll just quickly finish up here. One interesting sort of way to kind of turn it around and go from the rather than the theoretical side for explaining lambda is having an observational case for saying that dark energy can't be a cosmological constant. So maybe we need to make these more precise observations and show that what our best observations aren't consistent with a true constant. Maybe there's some properties of dark energy that are incompatible with a true constant. So something like the constraining the equation of state. There's another framework that's dealing with more complicated dynamics called the parameterized post-Friedman framework that I'm not going to really get into here. But the equation of state one's pretty easy. So the equation of state for a matter source is the fraction of its pressure over its energy density. There's matter, when we idealize in GR, matter has a certain value, radiation has a different value. A true cosmological constant has an equation of state of -1 everywhere at all times. And so one thing we could do is to try to constrain, if we could make an observational case that lambda, or that omega is not, W is not -1, then we'd have a very strong case that we need something beyond a constant, because the constant has to have W equal -1. So it's kind of making the case observationally that, like, look, there's an actual empirical anomaly that we could then ground our search for new theories or new models. So these graphs that I said I'd get back to, these are the one on the left is constraining the equation of state and the fraction of energy density due to matter. That omega m is the fraction of matter density or energy density due to ordinary matter. 1 minus that in a flat universe is the fraction due to dark energy. So what we see, there's observations from the cosmic microwave background is that red band, the type 1a supernova, those blue bands. The different bands are at different confidence intervals. So it's just 95% confidence intervals, the largest, and it gets smaller. And then the green is baryon acoustic oscillations. These are just sort of 3 major sources that I've mentioned for how we determine the cosmological constant. And it seems like when you combine all of these, you have a pretty tight constraint that W has to be pretty close to -1, and that the fraction of matter energy density is about 30%, which means that dark energy in a flat universe, which we have independent evidence for, that means that dark energy has a fraction of about 70%. It's, that's where you get that 68 point whatever number. The graph on the right is determining how much the equation of state could have varied in cosmic time. So as you go back in the evolution of the universe, this WA parameterizes, if WA is 0, that means there's no variation. That's a term they've put in to say that, there's W naught plus some variation term. And right now, all of the evidence, it's actually, there's a little bit, if you go to the center of all these combined blobs, there's actually maybe some evidence that the equation of state was smaller in the past. You have a negative WA. So like if it was here, centered on here, that would strongly favor just a true cosmological constant, still consistent with that constant, but there's some variation there. So this is a sort of different way of trying to make a case that we need some further explanation. Okay, so I'm gonna, so I'll just end here. One drawback to eliminative reasoning like this is that there's a sort of underdetermination. Just knowing that W is minus 7.5 or something like that rather than -1 doesn't tell you what that implies theoretically. It gives us, okay, it can't be a constant, but what else could it be? I mean, the possibilities are still endless. You still have some sort of underdetermination potentially there. So you get these underdetermination issues. I'm going to skip the underdetermination because David helpfully on Friday showed us how to avoid these. You shouldn't pay too close of attention to the predicate persistifications of the theory and just pay attention to the structural features. And you won't have to worry about any of these underdetermination issues. If you don't buy that there's going to be issues. There's equivalences and dualities between dark matter and dark energy as matter and as modified gravity. Turns out there's transformations between different types of modified gravity, so it's not really clear how to make sense of that. So yeah, this is all just about underdetermination, but again, for those of you at David's talk, we can hopefully deal with that. Yeah, so dark energy is an interesting philosophical ground because it's sort of cutting edge. There's a lot of room for disagreement, and philosophical sort of background assumptions on explanation, on confirmation, on what we think about theories are all playing a really central role in some of the debates about what direction to take in cosmology. So I'll leave it at that.
Can you take a 2-minute break and we'll have plenty of time for questions? Wow.
Yeah.